Okay, we're going. Okay, so last time, y'all recall we were talking about polar coordinates, and it's just another way to use numbers to describe where a point is in the plane, right? It's a pretty simple idea, a coordinate system. Again, we're very accustomed to the rectangular coordinate system. You've got to realize that it's just one of several options, and this is a different way to do it. So very useful, as we're going to see later on. I'm afraid it's going to be a while. I am going to show you one actually pretty cool application of coordinate systems today, but most of it's going to come later. Okay, so we talked about various aspects. They're not unique. There's this unfortunate ambiguity in notation. You got to be really careful with the geometry. You cannot just memorize reverse conversion formulas. They don't work. Right? Easy example. You get it wrong if you just kind of write down naive formulas that r is a square root and theta is arctan. It's just not true. Okay. So moving along. So equations in polar coordinates. So here are some, just a few examples. Some of them are easy. So r equals 3. Now this one you can analyze pretty easily. It's kind of thinking in polar coordinates. It's telling you that the distance from the origin is always the same. In some sense, it's kind of defining a circle, right? But if you, for whatever reason, didn't notice that, you can algebraically see it as well by just squaring both sides, realizing that r squared is, of course, x squared plus y squared, and then you really do recognize the equation for a circle from, algebra class back in high school, whenever that was. Okay. All right. So the point to this is the conversion from a polar coordinate equation back to a rectangular coordinate equation that you might be more familiar with. You can do something similar in this case. Suppose theta is pi over 3. Now again, side note. Yes, you can think of that in polar coordinates. That defines this angle. And r being allowed, of course, to be either positive or negative. We get that line. Sure, right, fine. But if you didn't notice that, take the tangent of both sides. And then recall that tan theta is y over x. And then this, again, recognizable as the equation for this line. Now, there won't always be such convenient little opportunities here to do this sort of thing. Sometimes there are, sometimes there aren't. I'm showing you the cases where it works out nicely. Do notice, though, that the goal, in some sense, of the algebra of my first step, right, is to create something in my algebra that I know how to convert into rectangular coordinates. Right, so that's kind of the strategy of what happened in these two examples. Okay, so now, again, sometimes it's just not going to work out. If you take this one here, for example, if you try to, get clever and write down a rectangular version of this, it's not going to work in any useful, reasonable way. What are we going to do about this? How do I make sense out of what this looks like? And roughly speaking, you're going to plot points. And I don't like to do them one at a time. It takes far too long. I like to think about sort of, small ranges of angles, sort of in groups. And so, for example, let's think first about these angles. Theta going from 0 to pi over 2. Those are those values of theta. So these are going to be theta going from 0 to pi over 2. Keep in mind that's theta. That's this right here. Notice then what that means is that the argument going into the sine function. Now you've got to distinguish. Theta is not just automatically what goes into the sine function. Here we're looking at sine of 2 theta. Right, so if theta is going from 0 to pi over 2, then the argument that goes into sine, the thing that decides how many oscillations of the sine wave we have, that goes from 0 to pi. Right? And as the argument goes from 0 to pi, sine of that argument goes from 0 up to 1 and back down to 0. And so now what you've got to do is you've got to sort of think through, all right, as I look at these various different values of theta, as I look in these various different directions, theta going from 0 to pi over 2. What does it look like when my r, my distance from the origin starts at 0, then increases up, and then comes back down to nothing? And well, it looks kind of like this. Here the r is increasing, and then it starts coming back down and makes it back down to nothing by the time theta goes from, again, 0 to the end of that range that we're looking at, namely pi over 2. Everybody see what happened there? Everybody good? You got to be careful with this kind of thing. The 2 is the what do you call it? Man, I don't want to say landmine exactly, but it's the thing that makes this a little tricky, right? But you can kind of motivate that the picture. The picture looks something like that, at least for those values of theta. All right, now real quick, I'm not going to go through the whole argument for the next chunk, but I just want to point out that for the next chunk of values, namely as theta goes from pi over 2 to pi, notice that r is negative for those values. And that means that as I look in these various directions, as I look that way and that way and that way, etc., for each of these, I'll be going negatively in those directions. So, for example, for this first direction here, going negatively, a little bit negatively in that direction puts me back to here. And then as I sort of move around these angles, I do like that. That's a little bit of a sort of, geometrically you just got to think it through. But that's what it looks like. So altogether, it's kind of elegant, really, that this curve starts at the origin, and you get what you might call a kind of a pedal like this going down like that, and then it just jumps down here into the fourth quadrant, and in some sense keeps going. And then you might expect that it would do like this, and you'd be right. And maybe that it comes up here like this. Yep. Indeed it does. And then it repeats. So that's what this looks like. All right. Okay. Here's another example. This one is prime for convenient algebra. Now you're gonna be tempted to see the r here and think, oh yeah, but I like r squared. I like r squared because r squared is equal to x squared plus y squared. So let's square both sides of this equation. And I guess you could. The problem is cosine squared then, what's that? Cosine squared is not conveniently writable in rectangular coordinates. So the better move, and this is, by the way, I didn't think of this. This is another one of these slick moves that somebody showed me. Now I remember the trick and I get to use it for the rest of my life. Same for y'all. Multiply by r on both sides. You still get the r squared that you want, right? You still get that. But now the right side of the equation has also turned into something that we can easily, immediately, directly turn into rectangular. And that gives you then an equation that is highly recognizable. You do have to, by the way, in order to convert this equation into this picture, you have to complete the square. Y'all remember that? That completing the square was already, even when I was in algebra class, kind of, going out of fashion or something, like, we've got the quadratic equation. We students don't need to learn how to complete the square. And it was already sort of like being poo-pooed. I think that's a tragic mistake. I hope maybe the world has turned around. Y'all been in high school much more recently than I have. Do y'all know how to complete the square? Okay, good. Well, I'm glad some of you at least have. If you're shaky on completing the square, namely what you would need to do to turn that equation into this equation, look it up. It's a neat trick. It's not hard. It's clever. It's not hard. But it's very useful. Here and there, and again, you never know what's going to come up. All right. Okay. Going the other direction, going from rectangular into polar. Well, one thing you can do is just everywhere you see a y, you put r sine theta. Everywhere you see an x, you put r cosine theta. After all, that's what they are. You just write that down, plug them in. However, sometimes you can pull a quick little fast one and save yourself some trouble. I could have called this r cosine theta, but instead, I'm going to square this out first. Notice then that I have an x squared plus y squared, and I'm going to save myself having to write down and then deal with a Pythagorean identity. Not that it's hard, but it's just a certain amount of pencil lead. I don't want to do it. Kind of a little convenient little shortcut to look for and capitalize on opportunities to save yourself that little bit of trouble. All right. What do you think? Everybody happy? Real quick, I want to encourage y'all to make sure to remember. I mean, obviously, I want you to understand the process, of course, right? That's the main thing. But also, really convenient to know how to write the polar equation for a circle centered on the x-axis that goes through the origin. You could think about how you would adapt this if the circle was bigger. Critical that it has its center on the x-axis. Critical that it has its touches, goes through the origin. But if it's a little bigger, a little further down, how would you adapt that? And then likewise, if it's on the y-axis, those are going to come up. Okay. Everybody happy? Are we good? Okay. Good deal. Okay. So cylindrical coordinates. Going to 3 dimensions now. Honestly, cylindrical coordinates, that's pretty much just polar coordinates. It's what I'm going to say. If you were to try to think of the most obvious way to use polar coordinates, but in 3 dimensions, very likely you'd think, well, look, if I have a point here, I can look at the projection down here into the xy plane. That's being as it is a point in the xy plane. I can write down convenient formulas for x and y. Just use polar coordinates, literally. Right? And then, of course, now there's also, though, the fact that this is, in fact, in 3 dimensions. There is also a z. Oh, whoa! What happened there? There is also a z-coordinate. So, I guess we'll use the r and the theta for what's going on in the xy projection, and then we'll just leave z there. Right? I mean, it's a pretty natural first cut at maybe how to make a 3-dimensional coordinate system. And very commonly referred to as polar coordinates in 3 dimensions. And I think that's fine. I still think it's easier to say cylindrical. Right? But anyway, you can call it 3-dimensional polar. I guess it's harmless. You notice you do get to keep all of your old identities relating x and y and r and theta. That's all the same because it's literally the same. Yeah. And then just don't forget z is there also. So a couple of easy examples here. You can persuade yourself. I'm going to leave this to y'all to think through that if your distance from the z-axis is always the same, then you get a cylinder. I think that's a pretty easy pitch. Now, you can convert, if you're looking at a sphere, let's say, here's your equation, rectangular equation for a sphere you all recognize. Notice you can use this identity here. Now the x and y are gone. Now you have an equation here that is entirely using cylindrical coordinates. Right? It's using r and z only. Now there's no thetas, whatever. So this now is the cylindrical equation for the sphere. So that's a pretty easy conversion as well. Okay. This next one, a little tricky. What do you do with this? Z equals kr. First, observe that this is a cylindrical equation, right? The only variables involved are cylindrical coordinates. I like to think of this as follows, and that is, notice there's no thetas. And let's think through, what does it mean that there's no thetas in this equation. And I want to flash back real quick to when we were talking about equations of planes. And I pointed out that if there's no y's in your equation, then it's parallel to the y-axis. I can't draw such a conclusion here because there is no theta axis to be parallel to, right? But let me say it a little bit differently then. Back in rectangular coordinates, if there's no y in the equation, it's like you're just sliding something. You can slide it all you want in the y direction and nothing happens because y doesn't matter. So likewise here, if there's no thetas, then you can rotate in the theta direction all you want and nothing happens. In other words, it's rotationally symmetric around the z-axis. So no thetas means it's rotationally symmetric around the z-axis. And the nice thing about things that are rotationally symmetric is you can just pick any cross-section then. Let's just think about, I don't know, it doesn't really matter. Let's pick this cross-section that contains the z-axis. If I can understand what this surface looks like in that cross-section, then sweet, and I'll just rotate it around and victory. Right? All right, well, what's the equation in that plane where theta takes on a certain value? Doesn't matter what theta is, so the equation is literally still the same. It's still z equals kr, and that is an easy plot to make. So in this plane, we've got a line. Now, don't forget, r is allowed to be negative, right? I'm allowed to let r be negative, and it has to be when z is negative, right? So we get the whole line, not just the sort of the positive part. And now I appeal to your intuition. That's what it looks like in one plane. Imagine what that looks like when you rotate it around, as we previously discussed, and you get this cone. You might call this a double cone, right? But this is really more naturally thought of as just naturally what a cone is. Okie dokie. Okay, a real quick warning. There's a temptation that whenever you have something that's round, right, there's a lot of round things, cylinders, circles, spheres, a lot of round things. When you have something that's round, you need to talk about its radius. When you're going to give a name to the radius, it's very natural, very common. People want to use r to represent the radius of your thing. So you're going to have to quit that. Can't do that anymore. R is now a variable. Right? And you can no more use r to represent a fixed, constant, given value that happens to be a radius of something. Then you can use x to represent a distance. Yeah, no, because x is a variable. I need x to be able to be anything, so I can talk about points, any point in space. Right? So likewise, you can't use r as a constant anymore either. So heads up about that. Now, if you want to instead use capital R, cool, or R naught, fine, or people will do all sorts of little weird random things. Any modification, that's all good, fine. But R itself is now a coordinate, cannot be a constant. All right. Okay, so that's all I'm going to say about cylindrical. Spherical is where it starts to get a little bit more challenging, a little bit more interesting. Spherical coordinates is also sometimes called polar coordinates in space. I think it's a big mistake. Polar coordinates pretty clearly has a lot more to do with cylindrical than it does with spherical. And you can't use the same terminology for both of them, so you got to pick one, and this is not it. Right? So please don't refer to this as polar coordinates in space. It's very significantly different from polar coordinates, certainly more so than cylindrical. Okay, so what is the spherical coordinate system? Here are the three variables. Oh, whoops. Here's the three variables. Theta, phi, and rho. Talk about them one at a time. Theta is kind of what you think. It's angle off the positive part of the x-axis, which, being as we are, of course, in space, gives us a what I'm going to call a half plane hinged on the z-axis. Hinged in the sense that one edge, the edge, I guess you'd say, of the half plane is the z-axis, and it turns kind of on that as a hinge. Does that make sense to everybody? Okay. So this part, to be fair, is just like in cylindrical coordinates. It's kind of polar-like. Okay, fine. Okay, what else? Now, once we've got a theta, what is this next thing? Notice now we have another angle. Second angle. And I'm going to say a little bit tragically, they use the Greek letter phi, pronounced phi. And I say tragically because, if you look at what these look like, oh my gosh, they look a lot alike. Please be very, very careful to not accidentally write theta when you meant phi and vice versa. Also, please be very, very careful. Don't give me any of, that. That really could, I don't know, is that a kind of a italic theta, or is that just a leaning phi? I really can't tell. Right? So I have to be able to unambiguously interpret what you write, so be careful about that. Okay, so phi is another angle. It's an angle measured off of the positive part of the z-axis, and then I'm going to say toward the theta half plane. So it goes that way. Again, with theta having already defined that the half plane, right, that tells you which is the positive direction for phi. And again, phi being the angle there at the origin. Okay. Oh, bad color choice. Sorry. Green. There we go. Okay, so that's phi. How we doing? Does everybody see what I'm talking about there? Now, again, angles can be positive or can be negative. What do you do if the angle phi is negative? If phi is negative, I'm going to say it's exactly what you would expect. If positive goes that way, toward the plane, negative just lean backwards away from the plane. And so a negative value of phi would just be kind of back this way, like that. A little hard to draw, but I hope you see what I mean there. Is everybody happy? Okay. Yes?
So when rho, it says how far in that direction?
I haven't gotten there yet.
Oh, okay.
Yeah. No, but ask me again in 30 seconds if I haven't answered the question. Yeah, go ahead.
What is the theta half plane?
Yeah, so the theta half plane, here, let me use my colors better. The theta half plane is the half plane hinged on the z-axis that's defined by the angle theta. So that's this half plane there. Is that cool? Yeah. Okay. All right. So now notice then, with a theta and a phi both defined. Let's see here. Theta and phi both defined. That gives us a direction. Right, in some sense from the origin, there's, if I've got this half plane and then I look at this angle phi, well, there's that, in that half plane, that angle off of north, you might say, that gives you, there's a single remaining direction. So that points a particular direction. And that direction, then we do kind of like we did with polar coordinates, this third, now that's not R, right, but it is a coordinate that represents how far you go in that direction, and so that then defines a point. And again, just like we had in polar, if it's negative, you just go backwards. You just go the opposite direction. Does that answer your question? Okay, yeah, cool. So that's called spherical coordinates. Arguably kind of a weird little setup. Massively useful in lots of situations. I mean, let me just try to give you a very quick idea of why this is useful. The world is full of spheres and balls. And if you want to describe a sphere, it's really easy in spherical coordinates. Rho equals a constant. Boom. Right? Super convenient. If you want to study something that is sphere-shaped, ball-shaped, right, then spherical coordinates is actually extremely natural. And a great example of this is the hydrogen atom. Right, so if you're doing quantum mechanics and you want to solve the Schrodinger equation for electrons in the hydrogen atom. Well, it's a very, very hard problem. Schrodinger equation, I flashed it on the screen first day of class. It's a pretty scary looking equation. And it's very hard to do in rectangular coordinates for a hydrogen atom. Fundamentally because all of the forces involved, etc., all the potentials involved, they're all really fundamentally spherical. They're all pointing toward the origin, right? And so by writing Schrodinger's equation in spherical coordinates instead of rectangular coordinates, it turns a nearly intractable problem into not that bad, highly doable. Because fundamentally, when you're dealing with spherical things, no surprise, spherical coordinates is going to be more useful. Right? So this idea, yes, it applies to the hydrogen atom, but, I mean, you could well imagine there's lots of other round things in the world. Right? We live on one of them. Right? So there's lots of instances where spherical coordinates just unavoidably natural. So it's a really useful thing. Okay. All right. So now, how do we convert to and from rectangular coordinates? The first thing I'm going to do, I guess I'd better zoom out for this. I'm going to focus some attention on this triangle right here. You can see that triangle is kind of naturally of interest, but I'm going to focus attention on it, since I want to pay so much attention to it, I'm going to redraw it where I can look straight at it instead of looking kind of askance, some angle. This is a little bit harder to see when it's kind of turned some half sideways here. So I like to just look straight at it. But so we're going to look at this triangle here, but don't forget, this is just a representative of this triangle in space that we're actually dealing with. So, all right, well, this angle right there is phi. That means that angle is phi. And I can think about the trigonometry of this triangle, where, of course, that distance is rho. And if you think about it, that distance there is z. And let's see here, this distance here is r. So this triangle right here, the trig of this triangle, is all we kind of really need to figure out. So first observation I'll make is that this r right here, pretty easily pitched, rho sine phi. Right? High school trig. And once you know that r is rho sine phi, then you're really most of the way there on spherical coordinates, because we already knew that x is r cosine theta and y is r sine theta. So, boom, right? That's a really quick little move there. Just make sure to interpret r in spherical coordinates, and that allows you to use stuff you already know to understand x and y in spherical coordinates. Okay. And then, of course, now there's the other side of the triangle. This is rho cosine phi, and that is, of course, the other rectangular coordinate. So x, y, z, no problem. Here's the formulas. It all really comes off of this triangle, this real simple little triangle there. Pausing. What do y'all think of that? Does that make sense? Yes.
And then theta would be given?
No, theta is a coordinate. This is just converting from one coordinate system to another coordinate. These are just relationships. And so, yeah, maybe rho, phi, and theta are given, and you're solving for x, y, z. Or maybe x, y, and z are given, and this is your sort of foot in the door to trying to figure out what's going on with rho, phi, theta. Yeah. But these are general relationships. Now, I encourage y'all to do two things. One is make sure to understand this triangle and this reasoning. This is how, in my entire life, and as much as I've used spherical coordinates, and it's all been a lot, this is the only way I've ever understood spherical coordinates in relating to rectangular coordinates, because it's a picture and a concept. It's a strategy, right? And I can remember those kinds of things, and I'm really bad at memorizing formulas. I would never trust myself if I just memorized. I would never trust that I was remembering this correctly. I'd be like, oh my God, is it rho sine phi, or is it rho cosine phi? Which way does it go? Right? If you just memorize, you're going to get it wrong at some point. So please make sure to understand the picture and the argument and the strategy there. And the second thing that I want you to do is to also memorize these formulas. Because you might be better at memorizing than I am. And when you're taking a test, it is nice to, as you're taking a test, to just have those formulas just boom, locked and loaded, ready to go, and just instantly write them down. It'll save you the 10 seconds that it'll take you to think this through. Right? Okay. All right. Okie dokie. So, a couple of examples. Again, no surprise. Here is a sphere. And so, setting rho equal to a constant gives you the equation for a sphere. I mean, it's a pretty easy observation there. This is why we call it spherical coordinates, by the way. The equation of a sphere is just, coordinate equals constant. Remember how we talked about the failure of uniqueness of polar coordinates? Well, we have a similar but worse problem with spherical coordinates. So with polar coordinates, I'm going to loosely say that there were two different ways to write a point in spherical coordinates, and in polar coordinates. And of course, it wasn't actually two. It was infinitely many different, because you can go around 2 pi as many times as you want, and in some sense, nothing happens. Right? The directions are all the same. But there were two really different ways, because with polar coordinates, I can go that way by pointing that way and going a positive r, or by pointing the exact opposite way and just going negative with r. So there were kind of two different classes of polar coordinates, you might say. With spherical coordinates, there are 4. So in particular, let's think about this point right here. That details given, right? Here's the rectangular coordinates. But notice that there are 2 values of theta that you could pick. Theta could be kind of like this, or theta could be the other way, right? I could think of this purple point as what you get to with theta being that way, and then just choosing phi to be negative. And just lean back, face in the dark green direction and then leaning backwards. That still gets me going the correct direction. Right, so I have these 2 choices of theta. And then now, here's the thing, with each one of these thetas, I have 2 choices of phi. So phi, for example, let's think about this, sort of the relatively easy natural choice of theta there. Phi could be positive, like that, or just as well, phi could be negative, like that, and then I could, go a negative rho in that direction and a negative rho in that direction. So we have 2 thetas. for each of which we have 2 phis, and that adds up to 4 different ways to do it. And I think a really nice exercise, I want to encourage you all to do this, is to write down all the details for all 4 of these options. And don't worry about the, plus multiples of 2 pi, right? Just think through the rest of it, though. And then compare with your classmates, and if you disagree, then you have something to discuss, something to debate. And if you can't resolve your differences, then come to office hours or the help room. Right? But I think this is a nice little exercise to cut your teeth on spherical coordinates. Okay. Everybody good? All right. So here's the one little cool application I'm going to give you. I think this is neat. You may have already noticed this, but at least the angles of spherical coordinates kind of relate to longitude and latitude. They're not exactly the same, but if you set up the globe just so, then theta is east longitude. All right? Everybody know longitude and latitude on the... Yeah, okay. And then now, okay, we have a different story with latitude. Latitude's not the same as phi, but latitude, north latitude, is like that, whereas phi is like that. And I think you can see that these 2 angles always add up to pi over 2. Okay, so the fact that these are always pi over 2 means that you can relate those angles like that. So if you know longitude and latitude, then you know spherical coordinates. I mean, I suppose there is the remaining, yes, you also need to know rho, but if you think about it, rho, everywhere you are on the surface of the Earth, you are pretty much exactly 1 radius of the Earth away from the center. Right? So if you know longitude and latitude, then you know spherical coordinates. Okay, so why is this useful? I think this is a really cool trick. Again, I wish I'd thought of this. I did not. Somebody showed me this. It's very clever. But let's ask this question. Suppose I have 2 locations on the surface of the Earth. So there's one spot. Maybe that's, Oslo, right? And then here's Durham. All right, so how far is it to Oslo? Well, it's a tough question, right? You can't pull out a map and draw a straight line because a straight line on a map is not a straight line. Not only that, but a straight line on a map is not even the shortest distance. It's just not, right? Mercator projections are famously distorted, right? And that's why, if you look at a Mercator projection, you'd think Greenland is bigger than, Africa, right? Which is not even close. Highly distorted, can't trust it, and straight lines are not shortest distances. Mercator projections stink, certainly for these purposes. So how would you measure the shortest distance? And, one thing to do is to think about, oh my gosh, I could consider all the different spherical paths, and, ooh, man, that seems like a hard problem, until you realize that no, all you really need to know to get that distance is you really just need to know this, let's see, color choices. You need to know this angle. And if you want to understand that angles you can understand with dot products. Dot products you can compute super easily with rectangular coordinates. Right? Rectangular coordinates you can get pretty easily from spherical coordinates, which you can get pretty easily from longitude and latitude, right? So this little observation that we made right here, that you can that you can connect longitude and latitude to spherical coordinates, that's the foot in the door that allows you to then find the rectangular coordinates, take the dot product, relate that to angle, and therefore compute distance. And it's just not hard. There's details and arithmetic, right? But it's a very straightforward way to compute the shortest distance between 2 points on a sphere. Neato trick. Everybody with me? If you want to see an example of this, by the way, I did make an exam question at some point in the last year. I've forgotten exactly when. So you can look up that old exam question and see the solution. Okay. Does everybody know that I have all my old exams online? Okay, just to make sure. And then not only are they all my old exams, but also solutions as well provided. So I think that's great study material, and I hope you make use of that and however you think would be most convenient, most useful. Okay. All right. And now this one, I'm going to be really quick with this. This is just like in polar coordinates. It's just 3 instead of 2. But again, if you have a rectangular equation, you can pretty much just plug in. But do look for opportunities, for example, to take something and expand it out so that you can then identify where some of the trig work has already been done for you. Capitalize on that. It's very convenient. And then, of course, you do have to, let's see, I guess we have to cancel these ones. And then don't forget that x is that. So you have to know those conversion formulas. And then solve for rho. And here's your spherical equation for that sphere. Okay. Yeah? Okay. Right. All right. So now this last little bit I'm going to be very quick with. We've talked about standard basis vectors before. That is, we've talked about rectangular standard basis vectors, and these are they. And I know you've seen these in Math 218 linear algebra. I like to write them as E1, E2, E3. It's very standard, by the way. I didn't make that up. But you might have seen them as IJK previously. Fine. Again, it's fine for 3 dimensions. You're going to get in trouble if you do anything in 17 dimensions. But anyway, so those are both notational options. They're great in a lot of ways. Linear combinations, for example. Right, rectangular. We've already sung the praises of rectangular coordinates. Good stuff. But there are similar ideas that you can do in other coordinate systems. And the idea in particular is that think of standard basis vectors as unit vectors pointing in the direction of increasing a single coordinate. So, for example, if you're here at this point and thinking in polar coordinates, increasing only r and leaving theta constant points that way. Okay. Unit vector pointing in that direction. And on the other hand, if you want to hold r constant and increase only theta, then, well, you're going to go around in a circle, but at least at that first instant, you're going to be going that way. Right, so this pair then of vectors, these are called the standard basis vectors. You might say the polar standard basis vectors at that point. And you can think through the geometry, and I think this is a nice exercise, a couple little geometric puzzles to think through when you write down the formulas for all the non-rectangular standard basis vectors. And I'm going to leave those details for you all to think through. It's a nice exercise, again. And they're in the book also. But anyway, those are what they are. The thing you have to be careful of with non-rectangular standard basis vectors is they don't have all the nice properties that the rectangular ones do. So for one thing, they're not constant. Right? E1, the rectangular x-coordinate standard basis vector, it's the same everywhere. All of those, every E1, no matter where you draw it, they're all parallel, they're all same length, same direction, they're the same vector. It's literally a constant. Not so with polar, right? You look at this picture here. ER, for example, is that direction at that point, but over there, it's like that. And these are not, oh man, stylus. These are not the same. So, that's annoying. Also, they don't play nice rectangular coordinate, linear combination rules. So, for example, coordinates in rectangular, coordinates are coefficients in a linear combination of standard basis vectors that gives you that vector. Again, this is a really basic fact of linear algebra, easily checked by just writing down, well, the formulas for E1, E2, E3, real simple, zeros and ones. You multiply this out, and you get X, Y, Z, right? It's not hard to do. Very handy. Every vector can not only be written as a combination of the standard basis vectors, but in a consistent and convenient way. And it's just not true for let's say spherical coordinates, right? Those coordinates are not going to be coefficients in a linear combination of standard. It just doesn't work. So don't get too into be careful, be cautious, exercise restraint when you're using spherical or polar standard basis vectors. Real quick, they do happen to be orthogonal. That's kind of a lucky convenience of the three coordinate systems that we use. They don't have to be. It's not part of the definition, but they conveniently are, and that's nice, but it's coincidence. Okay, so why are we talking about these standard basis vectors? What are we going to do with them? Well, there are several things that we could do with them, but we just aren't actually. So this is a kind of a dead-end topic. I need you to know that these things exist. I think it's a good exercise for you to have thought through. For example, in spherical, think through why these are the formulas for those vectors. Good geometry challenge. That said, we're not actually going to do anything with them in this course. So, like I said, kind of a dead end topic. But you need to know that they're there and what they are. Okay, so that finishes chapter 1, and we move on now to chapter 2. We got 3 minutes. I'm gonna just do a couple of quick things here. First of all, I want to there's a certain amount of lingo that we need to straighten out, introduce, fix, case may be. We're going to start off with a function. I know that you've heard the word function before, but I think most students at y'all's level, I don't know about you in particular, but actually misunderstand what precisely a function is. Even this is, by the way, not as rigorous as it could be. But appropriate to this class, here's what a function is. A function is a trio. It's three things together. And that's important. It is all three. If any one of these things is missing, then you don't technically have a function. You need all three of these things together to make a function. The three things are a domain. That's where inputs come from. What I like to call a target. That's where outputs go to. Right? That's what, if you think about it, and this should track with your understanding of function. Functions take things from over here and put them over there. Well, the bucket that they come out of is called the domain. The bucket that they land into is called the target. And then there's what we call the rule of assignment, and this is what you might think of as being the formula. This is the rule that defines exactly what the output is for any given input. So sometimes it's a formula, but to be point of order, it does not technically have to be a formula. So a couple of examples. Here's an easy one: natural log. Y'all know that function. Here's where it's defined for positive real numbers. And when you take the natural log of a positive real number, you get a real number. So we have here domain, target, rule of assignment, and how you define log is, there's various ways you can write it down. That's not what this is about. Okay, here's a more interesting example, I think, though. Let's look at these three functions here. All of these three functions have what I'm going to call the same formula. It's the student ID number. Now, is that a formula? How do I write student ID in terms of exponentials and polynomials? And that's not what it is, right? It's not a formula per se, but this is a well-defined rule. of assignment, right? You give me any student, I can produce an integer that is that student's ID number. Rule of assignment. Is that cool for everybody? Okay, so rule of assignment. So all three of these functions that I have listed here, they all have the same, what you might call the same rule of assignment. Very tempting then to say that these are all three, FGH, all three the same function. They are not. F and G are different because F and G have different targets. Now that seems so silly. We're looking at the same students. We're getting the same student ID number. Right? But not just being uptight and formal about this, but here I was requiring that student ID number be an integer. Here I am not requiring that it be an integer. It is. It always will be, right? But I'm not requiring it. And so this is a different target. That makes it a different trio. And so these are different functions. F and G are different functions. In a, uptight, precise, rigorous sense. And then likewise, let's look at G and, F and H. Yeah, F and H. So F and H have different domains. So the student ID function, if I say the student ID function is defined for all students at the whole school, okay, that gives me a function. If I say, but now, okay, listen, I only want to define, still student ID, still an integer, blah, blah, but I only want to define it for students in this section of this course. Different domain, different functions. And this distinction is going to be important next time. So we'll end it here. See y'all later. Have a good